right, so welcome to this recording about the first example of pysheaf. I'm going to open it with idle. Sometimes you have to open idle in order to open the file. Sometimes some of your systems like mine, you can just right click and open with idle, or whatever environment you're working in is fine. If you find that you can work at a command line, so if you, let's say, you can type Python or Python 3 and your Python comes up and you can do everything you need to do in a command line environment, but you can't do it in idle, then you have a path problem. There is a official way to fix that, but what I usually do with my students is normally if you uninstall and reinstall your idle, it usually just works. Here, I found a screenshot at the Towards Data Science website. This is the window you're going to look for when you're installing Python. Make sure you check this second box. It is unchecked by default, but it should be checked in my opinion because it causes so much trouble for my students, because then they can't get Python to work, and it was just because they didn't check this, and it's so hard to fix it after the fact if you don't check it right there. So that's my recommendation, honestly. Just uninstall and reinstall, and as long as you check that box, you will probably get rid of your path issues. So I just found this random example of a regression line on the internet with 8 dummy points and some kind of regression line. And this is the kind of thing I want you to have in the back of your mind that we're going to try to model. And at the end, you can actually do this example and see if you get this result back out. I'm not going to do this example. Instead, what I'm going to do is an even dumber example, world's dumbest regression line example. It only has 4 points, and you can see the regression line is y equals 1 plus x. And here are the 4 points we're going to try to fit a line to. Okay, so that's the model we're going to work with right now. And we're going to build a sheaf to do this. So what do we need for a sheaf? Well, we need a directed acyclic graph. And let me tell you what that is. Hold on. Okay, a picture is worth 1,000 words here. So a directed acyclic graph has nodes represented here as circles or ovals, and they have edges or arcs. Okay, and the thing is, you can't have a cycle. So for example, it's okay if you have, let's say, there is a bit of a cycle if you ignore the arrows. You could make a circle here, but you have to honor the arrows. So given that we're honoring the arrows, you can't come back to a place where you started. That means it's acyclic. So you can usually stretch them out into a nicer way of looking at them with a little bit of effort, but it doesn't have to be planar. This one is planar, but it just has to be acyclic and is a directed graph. Okay, so let's say we have a directed acyclic graph and we have nodes and edges. On the nodes, we're going to have some sets living there. And on the edges, we're going to have functions which go between those sets. So if you go from A to B like this, a node to another node, you have to put a function on that arrow. Okay, there's a slightly better picture. So A could be a node, B could be a node. We have a set living on A, a set living on B, and on the function on the arrow, we put a function that tells us how to go from A to B. All right, and this other thing called path independence. So if I had another node C and I had some arrow going from A to C and C to B, it shouldn't matter which path I take. When I end up at B, I should have the same result. So let me give a silly example. Okay, here's a very silly example, but maybe we're just dealing with the set of real numbers, and to go from A to C, you multiply by 2, and from C to B, you add 17. Well, then to go from A to B, you pretty much only have one option. You multiply by 2 and add 17. It's a very silly example, but I just want to stress the point about path independence. That's one of our conditions, and if we have all those conditions, then we have a sheaf. So, warning, some of the data that you're working with will be baked in with the sheaf. That'll be kind of part and parcel combined with the sheaf itself. and then some of your data you're going to have to add in later as well. I'm adding data. And the best practices is that you create the sheaf and then you add the data, but from a coding standpoint, you can potentially do some of each as you go along. But just for best practices, we're going to create an entire sheaf and then add the data. So it may seem a little bit counterintuitive, but that's the reason for that. You have to rethink your ideas about how information flows, and we'll get into that with some of the other examples. You start with a problem that you know the answer to, if you can, even if it's a dumb model with a very small amount of data, just so you can get your mind wrapped around how your sheaf is going to work and how you're going to make everything fit together properly. So this silly example we have, I'm going to just put all the data right out there so we can look at it and try to figure out how the pieces flow together. Okay, now I have annotated this model in gray with everything I'm going to have in my data and everything my final solution is going to give me. And I want to really understand what's going on and how the information is flowing. So normally we would think in terms of, hey, if you have 4 points, then they kind of determine what the best fit line is going to be. But that's not the way it's going to end up working in our sheaf model. The data is actually going to flow the other way. And let's think a little bit about why that's going to happen, okay? So the data are not in dispute. The data are whatever they are. We can't change the data. So that's fixed. And that is going to have to be part of our model or part of the initial data that we feed into the system, but it's not up for dispute. However, the best fit line is the part that we don't really know. We are thinking in terms of y equals mx plus b, and we're thinking about, well, we don't know the direction this line is going to go, but there's some points, and as we move the line, these distances are changing. These distances are what we want to minimize, and so what is it that we're actually doing is that as we are moving the line, we're changing the predicted value of those y's. So just to be clear, you know, maybe it's a while since you've taken basic stats, but the xy is the given data, but y hat is going to be your predicted data. So this would be, let's say, y hat would be over here. So this is x, y hat, as opposed to where the real data live. So as you change your best fit line, you're going to change y hat over here. So y is 1, but y hat, so x is 0, y is going to be 1, but y hat is what keeps changing. Okay, and it's going to kind of live over here too, but we don't have to know that because that's kind of hidden in the sheaf for us. So what we really have over here is we have y equals mx plus b, and what's free to move around is m and b. So that I'm going to say is dimension 2. And those are the two things I have to look for. Now, once I fit m and b, what is y hat going to be over here? You can ask yourself, what is y hat going to be? X is 0. Y hat is just going to be b, because x is 0. So over here, y hat is going to be 1.5 times m plus b. All right. Okay, and then I've written those in. You have all the predictions you want based on m and b, which are free to change. Okay, then what happens? Well, then you're going to measure a difference between your predicted value and your actual value. Okay, and those are all the squared differences. So it looks like the data are actually flowing along this direction, because once you pick the m and b, and that's what's going to be optimized, then these differences between the actual data and the predicted data, those are going to be determined by the m and the b. Okay, so we have our data, but it's kind of embedded in here in some sense, and we have to figure out how to build the model in pysheaf now. Okay, so we compare the code and try to understand what's going on here. When you're writing pysheaf, first of all, what you want to do is start with your obligatory imports. That's always the same. And then you're going to create a pysheaf, and you can just call it SHF. You can call it whatever you like, but we're just going to use SHF for all our examples. And we're going to use the norm type 2. My computer is not cooperating. Okay, I guess I can't touch my screen. Interesting. Okay, so I take my imports as always, and I name my sheaf. And the default norm we're going to use will be max, but we're not going to use that. We're going to use the L2 norm, which is what we normally use when we're doing least squares regression. So we're going to be looking at the sum of the squares of the differences, and so that's going to be chosen by this option that I just picked. Now, we're going to next add the cells and then the edges. The edges are called cofaces. We're going to add the cells, which is the points or the nodes. And we have 5 of them. We have 4 points, A, B, C, D, and we have L. So you may think that you should have 2 dimensions of data in your points, but we're actually not thinking of it that way. We're only actually thinking of the data as being the second part of the ordered pair. Again, this has to do with the way least squares regression works. When you're doing a least squares regression, again, you have the y hat and the y, and this is the only direction we're looking at distances. We're not looking at any x distances, so we don't have to think of x as being any kind of variable. Hopefully that makes sense. If not, think about it for a while, and eventually it will make sense. Okay, and so the 0 part is actually just part of the green, this green expression here. Part of the models we're working with are going to essentially hold that other part of the information. Okay, so this is going to be 1 dimension only. Okay, now I've noted it on all 4 points that we have 1 dimension. So everything here inside, this is the data that's being held, that's being held, that's being held. That cannot be optimized. We're not moving that. We're not moving the x's either, but we're going to hold them in the model itself rather than as data in our co-sheaf or data in our cell. We're going to hold that separately, just structurally. Just reopened the code in a text editor so I can touch my screen better. And when I go to run it, I'll open it back in idle again. Okay, so sorry about that. Okay, so let's try to figure out what's going on in terms of the functions. What are these functions that we need to make our cofaces all work out? So let's look at this example here as we're going from L, our best fit line, to point D. So what I need to do is, if I have M and B, how do I get the y hat? Well, I say 3m plus b. I already have this written out. This is the thing we've been looking for, and it goes right on top of here. So let me just rewrite all those lines where they belong. Okay, so that's where they belong, and I can get rid of these green jottings because the sums of the squares of the differences is something we no longer have to worry about. We had to worry about when we were trying to figure out least squares regression, but now we're going to let the sheaf take care of all that and simply tell the sheaf we're dealing with an L2 norm, and then the sheaf will do that for us. So I'm going to get rid of those jottings. Okay, looks like we have ourselves a sheaf, so let's just double check our conditions and make sure everything is right. So what were our conditions? We need a directed acyclic graph. Sure, we have that. We have to have sets on the nodes. Let's figure out what the sets are. I think it's just the real numbers. and the edges are functions, and we have path independence. Well, we have path independence trivially because we really don't have any way to get to the same place twice. So we have that. And do we have functions here? Yes. So we have 2 dimensions of data, that being M and B, and it feeds into point A and gives us 1 dimension. Yes, that function turns R2 into R1. That's what it's doing. Okay? Each one of these functions is doing that, and we successfully take the 2 variables that we can change, and we are going to then use that to find out what the y-hats are. And as you can see, again, the x values are kind of embedded in the model itself. So you see the x values are hiding as slopes in the functions that take the best fit line over to the predicted values. Okay, now let's see how that all gets coded up. And then we'll try running the code and see if it completely collapses or if it works. Okay, so first of all, we have over here in this part of the code, we're going to put all of our nodes, and then we're going to build our cofaces, and then if you want, you can see what it looks like. Now, I really honestly do not like Network X because I think it makes the ugliest graphs ever, but the good thing is you can just peek at your graph and see if it looks plausible, and then if it looks really horrible, you know that you left something out of your code. So it's mostly there. In my mind, it's just there so you can check your work. Okay, now you continue and you go ahead and put your data on, and that's all the blue circles in my diagram. And the next step is to maximally extend all the cells, but we have such a simplistic model. We have just this one thing, L is pushing data outward, and so we don't actually have to extend everything. We really only have to extend L in this example, and that will happen in one of our other examples too. All right, at that point, you check your consistency radius, and that's that magical thing which should be 0 when everything is balanced as well as it can be. So when you found the best fit line, your consistency radius should be 0, and since we can apply this other trick, we can start with everything the way it's supposed to be, then we can see if we can start with a consistency radius of 0. Again, this is just for getting your model up and running and making sure you coded it correctly. Then what we're going to do is figure out what's allowed to be optimized, and we've kind of already discussed that. We are allowed to change only 2 things. We're only allowed to change M and B, and so we can optimize this. Optimize me, yes, please. And then the points we can't change. So we have to basically say, do not optimize the points. Lucky for us, that is the default status. So the only thing you really have to flag is what can be optimized is true. Everything else is going to be default off. So I can optimize this one cell. When I'm done with all that all the magic happens in Fuse assignment, and then the last little block of code is just printing out what happened. Okay, so let's go ahead and see if this code works or if it just is going to blow up in my face. All right, we're back in idle or some other Python environment, and I'm going to go ahead and run this. Oh, I forgot to show you what the plot looks like. I usually comment that out because it's ugly. It's not too bad this time. So I look at this and I say, yeah, that's what I asked it to do. Okay, good. And what have I got here? Well, actually, it started out with a bad consistency radius, and it got down to a good consistency radius. Okay, and is that the right best fit line? Yeah, it looks like the best fit line to me. I don't know why the consistency radius is so bad, but anyway, I got a slope of 1 and an intercept of 1, which is what I expected. And so let's see what happened down here. Maybe I didn't start with, aha, I didn't actually start with, I don't know why my mouse is acting up. I really don't. This is not normal. But let me try putting the best fit line in from the get-go, So I know this is the correct best fit line, and I'm going to go ahead and run this. And then I see that it does not move off of the desired best fit line. It actually stays where I put it, and that's what I want to see. I want to see that if I give it a problem that's already optimized, it doesn't move off, and if I don't give it a problem that's optimized, it tries to move to the correct solution. Okay, so I'm happy with this. I am not happy with my mouse, but I'm happy with the Python, and so I'm going to suggest, if this makes sense to you, that you take the code for example 0 and you rework it so that you can do this problem. This one, try feeding it these 8 points and see if you can get back that regression line. Again, start out with your slope being 0.0908 and your intercept is 16.3. Make sure you get a low consistency radius and then move off of that, like give it a different regression line and play with that. See how far away you can go from the true regression line and see how bad it has to be before you break it. Because you could end up with something, if you say the regression line is 1000x plus 1000, maybe it won't converge. So it's something that you have to kind of play a little bit with and see where the limits are. Sometimes it will work really well, sometimes it won't. And there's also a way of telling it how many iterations you want. So what can happen is maybe you partially optimized it. Well, go ahead and fit those values, put those values back into your code and run it again. Or we'll talk later about how to change that maximum iterations value, and then you can bypass that. Okay, so that's a lot to think about. I hope that was useful, and I'll see you on the next video. Bye.